In this video, we will go over how to solve a finite element method problem in Python. So we'll specifically look at a one-dimensional problem and how to solve it. So this is the problem that we're dealing with. Here we have a system which has 4 nodes, 0, 1, 2, and 3, and then 3 elements, 0, 1, and 2. Okay. In each node, we have some force applied. So we have 10 newtons applied here. We're gonna call all our loads as P and our nodal displacements as U. Nodal displacement is how far does a node move after the load has been applied. So this is the displacement. Okay. Now there are things that you need to know about the problem before you can get started. So this is like the initial information. So we know there is some load applied over here. So we'll call this P1 equal to 10 newtons. And we also know at node 2, there is a 4 Newton force applied. So P2 equal to minus 4 newtons because of the change in direction. And then we have P0 here and P3 here, both of which are reaction forces. And we do not know the reaction forces yet. The objective of the FEM problem is to solve for these reaction forces. So these two are unknowns. Okay. Now if we come down and talk about the displacements, we have node 0 over here and node 3 over here, both of which are embedded in the wall and they are not going anywhere. So we do know the position after the load has been applied. The position of U0 is still going to be equal to 0. It's not going anywhere. And U3 is also going to be equal to 0. Okay. U1 is going to be unknown. We do not know by how much it's going to shift this way. And you could also imagine U2 is going to move a bit after the load has been applied. And U2 is also unknown to us. Again, the objective of solving the FEM problem is to find the unknowns. So we need to find this value here, this value here, this one, and this one. And that's what it means to solve the FEM problem. Now, one thing you should note is for every node, you have two information, the load and the displacement. In order to be able to solve the FEM properly, for every node, there should only be one unknown. So, for example, if you look at node 0, you will see that the load is unknown, the position or the displacement is known. If you go to the next node, the load is known, but the position is then, or the displacement is unknown. And this pattern repeats for the rest of the nodes as well. So this has to be valid for you to be able to solve the FEM. So make sure that this information is given. Now, there might be some cases in which there is no load applied, for example, on node 2. In this case, the load applied node over here is not unknown, but equal to 0 Newton. Okay. So just keep this in mind when you solve FEM problems. So the first task is to define our elements from the figure into Python, and the same thing for nodes. Okay, so we have to define both of this in Python. So let's see how to do that. So first, I'm going to import pandas to create data frames for nodes and elements. Okay, so the way we're going to do that is we will say elements pd.data frame, and we're going to give it some data and some column names. What are the column names? So column names are the set of information that you want to provide for each element. So for each element, you would like to know, where does it start, where does it end. Okay, and then there are other information such as the cross-sectional area of the element, and also the material property of that element. Okay, so we have the geometric information and the material information of that element. So these will be our columns for now. We also need to know the length, going to be the length of the element. We also need to know the stiffness of the element, which we can then eventually calculate from all this information. Okay, so for now, let's get started with the information that we have. So columns, we need to know where does the element start, at which node does it start, and at which node does it end. And data is going to be a set of a list of lists in which each list corresponds to the element. And the way you enter this should be numbered according to what you see in the figure. Okay, so 0, 1, and 2. Or you have to be consistent when you enter this information. So the first element starts at 0, ends at 1. So you can just type in over here 0 and 1. And the next information is going to be area and material. I'm just going to put some dummy values over here just to solve this problem. And for the next element, I'll just make a copy of the row, put it here, put it here. We have 2 more elements. So the next element starts at 1, ends at 2. And the next element starts at 2, ends at 3, node 3. Okay. And we will just make some changes to these numbers. So we have some variations in the results. Okay. So these are my elements table. So let's have a look at it. And so this is the table of information that has that now we just translated this figure into a data frame. So all the information about elements covered in the figure is now here in the data frame. So the next information that you need to put is your nodes information. So we'll do pretty much the same thing here. We need to know where is the node located with reference to some coordinate system. So if this is your coordinate system, and this is x, you need to know exactly at which position each node exists, and it's given in the figure. So we just have to put that in the nodes table now. And the next information is about how much is the load applied on each node and what is its displacement. Okay, we can also enter this information into the table. So let's do that now. The columns will be the first node. If this is the origin, it starts at 0, so the coordinate for the first node is 0. So we have 0. Displacement, do we know the displacement of this node? Yes, this node is not going anywhere. The displacement is always going to be 0, so you just set it as 0. Now comes the load. Do we know the load at this point? We do not. This is the reaction, this node, we need to solve for the reaction load here. So reaction forces here. So we do not know this number. You cannot leave it blank. So just as a placeholder, we're going to use the np.nan. This will give you not a number. This is just going to be a placeholder to show that this value is missing right now. Okay. To be able to run this, you need to first import your numpy package. So next node is at 5 meters. So it's at 5 meters. Do we know the displacements? We do not know the displacement. So this time the displacement will be np.nan. And do we know the load? Yes, we do know the load. It's 10 newtons. So it's 10. For the next node, it's minus 4 newtons, and we do not know the displacement. So just quickly, if you have a larger table, then you have to quickly run through it to make sure that for every node, you either know the displacement or you know the load. You cannot know both, and you cannot have both as unknown. Okay? You won't be able to solve the rest of the problem. So now that we have both the nodes and the elements table, the next task is to find the length and stiffness of each element. Okay. So to do that, you need to know the starting node and the ending node and its coordinate, and the length is the difference between the coordinates. Okay, this will give you the length of each element. And for the stiffness, once you find the length, you can just find the stiffness using the material property and the geometric properties, the length and the area, and E. And you can solve for the stiffness for each element. What we're going to do is we will add these information into the table. So we'll just add another column here called length and stiffness and compute the information and plug it in over here. Okay, so let's see how we can do that. So to find the length, we will have to go through each element, find its starting node and ending node, and then find the coordinate of the starting node and the ending node. Okay, so let's do this backwards. So given E, let's say we take one element, dot location 0. So we'll just do an example with one element. It has a start node, end node, it has area and material. So to find the length of this element, you have to first know where does it. So you need to do this equation, absolute of . where are the coordinates stored? The coordinates are not stored inside the elements table. It's stored in the nodes table. So we have to have a way of accessing the nodes table, going to the right node. So for example, this element, it starts at node 0, ends at node 1. So you have to go to the nodes table, go to row number 0, find the coordinate, or go to row number 1, find the coordinate. How do we do that? So coordinate and coordinate start. So coordinate start is going to be the start node. Go to the nodes table. You can go to the nodes table using the location function, and then you can give it the start node and the column that you're looking at. So the column is going to be coordinates. So coordinate. This will go into the nodes table and fetch the value at this position. So whatever your start node is, so if it's 0, you go to 0 and then fetch the coordinate for you for that node. Okay. But we then now have to define what our start node is. So how do we know what's the start node for this particular element? It's just going to be E, which is one of the elements. Currently it's element 0, and you can index out the start value. Okay. So now that we have this, the end node is going to be the same, end node, and we need the coordinate of the end node. So let's look at the length and what do we expect the value to be. If you do the math quickly, the length is going to be 5 meters here. Okay, because the node here is at 5 meters, the node here is at 0 meters, so 5 minus 0, you'll get 5. Let's see if that's the case here. And run the script. This is end node. Yeah, so that comes out to be correct. So our code seems to be working fine, but we need to do this for every node in the every element in the table. Okay, so you can either write a for loop, or the right way to do this would be to use the apply method. For that, this entire entire script has to be written as a function. So I'll define this as compute length given any of the row and all this. So given any element E, this has to be able to compute the length, and then you have to be able to return this back to the function that calls compute length. So, and now to apply this on your elements table, you just say elements.apply and compute length. And if you try to run this, by default this will not work, because you have, when you use the apply function, it applies it column by column. You want it to apply every row, so you have to say, you have to use the keyword argument axis equal to 1. Okay, so if I run this now, there you go. So the first element is 5 meters long, the next is 10 meters, the next is 5. So just double check if this information is correct. So you can see 5, this is 15 minus 5, 10, and this is 20 minus 15, 5. So everything looks to be correct. But now we would like to have this information show up in the elements table. Right now it does not show up here. So what we could do is you could just say elements and then create a new column in it. And this can be my calculated length. Okay, these are my calculated lengths. You could then repeat the same process to define the, what do you call the stiffness given any element. But remember that this has to happen in sequence. First you have to find the length, and then you have to find the stiffness, because stiffness depends on the length. Stiffness. So what's the code for stiffness? You just modulus multiplied by A, modulus of elasticity multiplied by the cross-sectional area divided by the length. So you have and if you run this code, you should now see the stiffness value also show up in the column. Okay, so we forgot to change the compute function here. That's why you're getting the same as the length. So these are ways that you should be able to debug your code and fix it. So right now you don't see any errors. It's spitting out values as expected, but the values are not correct. So, okay, there you go. So these are your stiffness values now. Now that we have the length and stiffness, we can now establish the global stiffness matrix. To create the global stiffness matrix, we have to do the following. First, we have to define each element and its stiffness matrix. So for each element, the equation is going to look like this. where we have I as the starting point. This is the start and this is the end. And this is the equation, the two equations that defines both the nodal displacements and the loads. Okay, so this is the this is the local set of equations. We now have to combine this and create a global set of equations. The way we combine it is by assembling these local equations together. In order to do this properly, let's say you have two elements here, 1 and 2, and you get the local, you get the matrix from each element and then place it inside a larger element. This will be our global stiffness matrix. But this has to be done carefully such that these matrices are placed in the right location. For example, the element 1 over here starts at 0, ends at 1. So you have to find the right spot. So this is 0, this is 1, 2, 0, 1, 2. So it has to go exactly in this location here in the global matrix. And if you go to the next element, this one, it starts at 1, ends at 2. You go to the next set here, U1 and 2. So 1 and 2 and 1 and 2. So it goes in here in the lower corner. Okay, and it gets added up. So anywhere there is an overlap, the stiffnesses are going to get added up as seen here. Okay, and this is how you form the global stiffness matrix. So the way we're going to implement this is for each element. For each element, we will create the matrix, but we will pad everything else with 0. For example, element 1 will show up as K0 and plus, and then we'll generate another matrix for the next element, which is going to be, and we'll do this for the rest of the elements and just add them all up together to get the global matrix. Okay, so let's see how we can do this in Python. First off, we need to know how to generate the matrix. Okay, so first we need to know how big are the matrices. This is going to be the length of nodes. Now we need to find the stiffness value for an element. Again, we'll look at an example of one element and then learn how to do this for the rest. So E is going to be equal to elements dot location 0, the first element, and we know the stiffness of the element. So the task is to fill in our empty K matrix with the stiffness. So stiffness. Okay, so the objective in this particular exercise will be to plug in the value of 12 at the right location. So we then now need to know where does the element start and end. So where does the element start? So start, go to E start, and end, go to E end. So if you look at the stiffness, start and end. So the element starts at 0 and ends at 1. So we would like, so this is going to be 0, 1, 2, 3, and 0, 1, 2, 3. So we want to change this number to 12, this one to minus 12, this to minus 12, and this to 12. That's the objective here. So how would we do this? Now there are multiple ways to approach this, but the easiest way is to use the numpy function that allows us to do the following. So there is a function that you could use to index particular portions of this. You could do this manually as well if you would like. You could manually go in and change it, or there is a way. There is a function in NumPy called ix underscore. All you have to do is just give it your indices. So 0, 1, and 0, 1. It should be able to generate all the numbers necessary to index these 4 points. So that's what we're going to use here. So this will create like a multi-dimensional index, which you can then use to extract information from K or put information into K. So for example, K IDX equal to, let's put in 100 and look at K. So the error here is because our start and end by default pandas assumes that it's a floating value. This has to be an integer. You cannot pass floating values as indices, so you need to convert this to integers. The easiest way is just say as type int, and it will make sure that the output from these tables are going to be an integer type. So let's run this. There you have it. So you converted these positions to 100. Reset it, and instead of putting in 100, you just put the stiffness value at the right locations. Now to do this for every element, again, you have to convert this to a function. So I'm going to convert. So it is working, but it's repeating 12 because we forgot to remove this line here. This is only referring to one of the elements. So remove this from here, so that as every row comes through, it computes the information again and again. So let's run this now. Yes, so you have the first one is all 12, 12. The other one is 6.8, and the other one is probably here somewhere. Now, what's the end goal? We don't want them to be separate. We want to add them all together, right? So you could just store all your information inside another variable called k. And now k is a pandas data frame, so type, or actually a pandas series. Yeah. So you could then apply the sum function to add all of them together. And now you have your global k matrix. Okay. So k has 12, 12, 12, 6.8, and this number is 12 plus 6.8. And the same thing happens over here. Once you have the matrix, the next part is to split it into different parts. If you remember how the problem is set up, we have the U matrix or the U vector, the displacements. Now, within displacement, there are some unknowns and then there are knowns. And for every unknown displacement, the load should be known. And for every known displacement, the load should be unknown. Okay. So what we're going to do is we're going to take the K matrix over here and then split it into 4 parts. Now, the reason why we're doing that is then we have like 2 equations. So if you look at this line, you have 2 equations. So here you can see after splitting, you can then use the sub matrices and then solve for your unknown value first. Once you solve that, you can then plug it into the next equation and solve for your unknown loads. So you have your displacements and the loads. Once you solve for both of them, that's the end of the FEM problem. Okay, so it is important to split up your K matrix into these 4 segments. Now, this is just to visualize how things are. They don't have to come in a specific order. They could be mixed in, they could be non-consecutive values as well, but our code still should work. Okay, so let's see how to do this, how to do the partitioning. So for partitioning as well, we'll use the same function. So we now have our K matrix. Oh, wait, no. Let me reset it here. So K is our global value. So K is our global matrix. And you could still index particular parts of it out. So for example, let's say you would like to partition the first corner here. So 0,1 row, 0,1 column. And it should be able to extract those particular portions of this. Okay, so we'll have to do this for specific parts. We have to first know which part of the U vector is unknown and which part of it is known. How do we know this? You could go back to the nodes table and you can find that information over here. Okay, so the nodes are in order 0, 1, 2, 3, and you would like to have this equation in order as well. Okay. So we would like to know the index information for the unknown values, and we know that we have the displacement column here, and there are unknowns here marked as not a number. In pandas, you can find this using the np.isNan function, so .isNa function. This will tell you where the displacements are unknown. So this will give you the index for which displacements are unknown or which loads are unknown. You specifically want for the displacement column, you can just say nodes displacement. You can index out that particular column and then check which ones are known and unknown. Okay. So to keep things clean, we will use A as the index for where the displacements are unknown, and we can do the same thing to know where the loads are unknown. It should be the opposite of A, but just to keep our codes clear, we will find where the loads are unknown. Okay, it will be the opposite of it. Okay. Once we have this information, the good thing is you can still use K and np.ix underscore, and the function still works with Boolean index as well. It doesn't have to be integers, it can also be Boolean index as well. Okay, so we can use the same thing. So if you would like to extract, for example, KAA, This will be the top portion. So in this case, you can give it the A index for the rows and A index for the columns. And that's your KA matrix. Okay. And if you like KAB, you can do the same thing. KAB equal to, copy this one, paste it here, and B. KAB. So in our particular example, for the displacements, we have, these are unknown displacements, unknown displacement, 1 and 2. And these are known displacements, okay, 0 and 3. Just to remind you, this was how the problem was. These nodes 0, 1, 2, 3. These were known, these are unknown displacements. Okay, so it's not exactly in order like I mentioned before, but it doesn't matter. Okay, so when I say AA, it should fetch the unknowns and unknowns. So my unknowns are here and here, unknown. These are the index for the unknown, so it should extract this middle portion over here. Okay, and when I'm dealing with the known, so this would be my KAA, and my KAB would be this number here. Okay, and that's what you see here as well when I solve for KAB. So the split seems to be working fine, and we'll now move on. Once we have made all the splits, we can now solve the equations for unknown displacements and unknown loads. So unknown displacements is going to be U. I'm going to extract it from my nodes table, the displacement. Those are my unknown, these are my displacements, and then I have my loads. So now we just have to solve for the unknowns. We just have to set up equation 3 and 4. Those are the solution to this FEM problem. U unknown and equation 4. So now we need to know how to split U into P known, U known. So if you just want the U known part, U known part, how do we get that? U dot is an A, or U of A will give you the unknown part, so it should be the opposite, which is B. Okay, this will give you the unknown, this will give you the known displacements, and you can do the same thing for your load values. And so we now have U known and P known, and the rest is just matrix multiplication. So we will have U unknown equal to So that gives you some numbers. Great. Now that you have the U unknown, you can solve equation number 4. So just write out equation 4, which is P unknown. And those are your values. Now, as a final verification, now you want to plug this back into your nodes table. So I'm going to create a new table called results, which are going to be the same as nodes. And I would like to replace this with the values that we just found. Okay. Again, you can do the same thing. You can just say dot location. It was A, I believe. So this will give you the displacement which are blank. And then you want to go to displacement. And you want to replace this with the ones that you just found, the unknown values. Okay. So it has plugged it in the right spots. Great. Let's do the same thing for the unknown forces. And there you have it. You have your results. As a final check of verification, you might want to add up all the load values in your nodes. The sum should be equal to 1. So load and dot sum. And so it looks like we might have made a mistake somewhere. It doesn't sum to be 0. So let's look at the load values again. Okay, so it looks like we are getting some numbers that should have added up to 0, but we probably made a mistake in the signs. So let's go back and investigate. Yes, so our mistake is here. You can see now global K matrix, the negatives are missing. Okay, So we should not have plugged in k directly here. We should have made a matrix here of k. So here what is happening right now is you get the big matrix and then you plug in this as k, 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 and k. It should have been negative k and negative k over here. Okay, so let's fix this. You can do that just by multiplying your stiffness with, this is the first row, 1 minus 1 and then minus 1 1. Okay, and let's run this. Okay, now we have the negatives in the right locations. Let's do the partitioning again and let's do the solution. Okay, so there is another mistake as well we made. If you look at nodes, you'll see that we have overwritten the positions here. So if I do nodes dot is an a, this code no longer works because there's no empty values in your nodes table. Why did this happen? This is because I said results equal to nodes. So what Python does is it doesn't actually create a new copy of nodes. It just assigns a different name to nodes. So any changes that happens to results also happens to nodes. Okay. So this is not working because if you want to rerun your code, this will not work. Okay. So always when you want to make a copy, you have to explicitly state that this is going to be a copy. Okay. Now this is not going to work as of now. So we'll have to rerun the entire code. So go to kernel, restart and run all. And let's see the numbers. Yep. So if you now do sum, you should get 0, which confirms that the results that you found were indeed correct. So I hope this helps.